Well, thank you all very much for coming during a summer holiday break to listen to us. I haven't been in Korea for a while. I first came in the mid-80s, and then a few times after. But it's amazing on each visit to see the progress in your country, the infrastructure, and of course you're the leaders and early adopters of technology. So much so, for example, I'm not a big adopter of technology. I'm usually slow. But recently my son, who's an early adopter, persuaded me to try a BlackBerry, which I began to use. But it's an American BlackBerry, and our technology is too old. So no CDMA, so we couldn't use it here. So Korea is a leader in many of these things, and all in the last 30 or 40 years, which is a remarkable progress. And I have a few students from Korea who have been excellent students, and I'm happy that Professor Juhan Chun, some of whose work I'll talk about in the last topic, has been a wonderful host for me here, as well as the other faculty and a few students whom I met yesterday. So I said I had to give this talk in an abbreviated form about a month ago, and I am not able myself to correct the location, so I just left that there. So this is a talk about, it's a story, as you said, with not many equations. Anybody who wants more equations can always ask me. So let's see now. So the story is how different fields, results from different fields, quite different. One is radiative transfer, which means, for example, how does sunlight cross the atmosphere and heat up the earth? Those are the theories studied in radiative transfer. And statistical prediction, I'll talk about, more about that in electrical engineering these days. And how those connections led to new algorithms which can be faster than the traditional algorithms, and, for example, had applications in cell phones. That's what I'm going to describe. There are many other applications as well, but we'll start with that. So the story begins with two mathematicians. Actually, one famous mathematician you may have heard about, the father of cybernetics, among many other more important mathematical contributions, Norbert Wiener of MIT, and a German mathematical astronomer, Eberhard Hopf. And in the summer, Wiener used to spend time in New Hampshire, his summer home, and all his visitors would go there, and Hopf, of course, visited him. And Wiener had this habit, he felt he could work in any field. So each visitor he would ask, so what is the most important unsolved problem in your field? And so the answer was from Hopf that in this radiative transfer theory, there was an integral equation proposed by two equally famous astronomers, Milne in England and Schwarzschild in Germany, to describe this, as I said, propagation of sun's energy through the Earth's atmosphere was the basic problem, but an abstract problem. But no one knew how to solve that particular integral equation. I'll show you the equation later. It's not important what it is. However, the next morning at breakfast, Wiener came and said, I solved it. So Wiener presented a solution. It was correct basically, but some details needed to be cleaned up. But it was such a brilliant solution, using such a new idea for people, that though the equation was not invented by Wiener and not by Hopf, people call that equation itself the Wiener-Hopf equation, and the method the Wiener-Hopf technique. And the other unusual thing is, usually it's the tradition among mathematicians that the order of names is alphabetical. But as I said, Wiener's solution was so unexpected that they changed the order. And there was a short paper in German in 31 on this technique. However, the problem is that it was too difficult to carry out this solution. Even though you could write the formula down, a certain spectral factorization method related to the terms in the integral equation, something had to be factored. In matrix terms, it's a simple problem. Factor a matrix as the product of two triangular matrices, upper triangular and lower triangular. We know ways of doing it. But in infinite dimensions, this is harder. And the word spectrum, all of the electrical engineers know, but it is an irrational spectrum. In other words, not a ratio of two polynomials, but more complicated expression. So how to do it was not easy. So then, a dozen years later, another very famous Armenian, Russian, Soviet astronomer showed, by using, I said here, certain invariance features of the problem, that a solution could be obtained. You could solve this integral equation by replacing, which is a linear integral equation, by replacing it with a nonlinear differential equation. Now, you might think that you're going from a linear problem to a nonlinear problem, it's more difficult. But that's not so, because this is a differential equation with a given initial condition. And I will show some formulas a little later. But you know, any such equation you can solve numerically, because you replace the derivative, say the variable here is p, dp by dt, you replace it by the approximation p of t plus delta minus p of t divided by delta. That's the approximation of the derivative. And so is equal to something, the right-hand side, nonlinear side. Therefore, p of t plus delta is equal to delta times that right-hand side plus p of t. So you know, if you know the value of p of t, you know the value of p of t plus delta. Now p of 0 is known, so you do p delta, p2 delta. So it doesn't matter, it's only a question of calculation. So that was interesting. Now, when I gave this talk, I didn't explain what are the invariance features of the problem. Well, for electrical engineers, it was well known. It was less well known to radiative transfer. I don't know these days if they study transmission line theory in electrical engineering, but we used to. And there's a well-known result. If you have an infinite transmission line, lossless transmission line, it has a characteristic impedance. In other words, you put a voltage across the front of the transmission line and measure the current, and this ratio is called the characteristic impedance. Now, if you remove a section of that infinite transmission line and calculate the characteristic impedance after removing this section, it's the same, because there's still a huge amount of line. So the problem is invariant to removing portions of the line. And you can get some identity, if those of you remember, you can get some identity for the characteristic impedance by using this idea. Now the Earth's atmosphere you can think of as a transmission line also. And though it's finite, I mean mathematically you can assume it's infinite. So that was the idea that Ambartsumian used. I mean, without knowing about the electrical background. So I mentioned the last thing. Any equation of this type is amenable in principle to numerical solution. But there was too much work. The curse of dimensionality came into Ambartsumian's solution. The unknown function had three variables, two of space and one of time. So in order to find its values in a region of space, you must have a three-dimensional cube, you know, every point x, y, and every time t. And, you know, it grows like the cube of the size of the problem. That was too much computation. So then a few years later, a famous Indian astronomer, Chandrasekhar, further exploited this though he didn't do it that way, but he further exploited what electrical engineers would call properties of transmission lines to replace the Riccati equation for one function of three variables with two other coupled differential equations, nonlinear partial differential equations. But these are now functions of two independent variables, not three. Okay. So the dimension goes down by an order of magnitude. Instead of being n cubed for the three-dimensional problem, it becomes n squared. And that's a big difference. So the problems could be solved. And Chandrasekhar, but in those days, what were the computers? There were calculators where you had to turn the machine by hand. And Chandrasekhar wrote, he was famous for many things. He was going from India to England, in those days only by ship. And while traveling, he found a famous result about, in astrophysics, about white dwarfs. When will stars shrink to a certain size? And when he went to England, he presented it to Arthur Eddington, who was England's royal astronomer and the man who proved Einstein's theory of general relativity by going to Brazil and measuring the eclipse to show the bending of light by the sun. So he was famous. And Eddington wouldn't believe him and ridiculed publicly in the seminar that Chandrasekhar gave his idea, saying it's totally wrong. And Chandrasekhar was only 20-something years old. Well, I think 40 years later or something, maybe 15 or 20 years ago, Chandrasekhar got the Nobel Prize basically for that discovery which he did as a student in 1920. So, anyway, now he used to write many papers with 40 parts, 50-part papers, with Roman X, V, I, 1, etc. So, a friend of his wrote a parody of his work, very interesting parody. He can give you the reference. But then he says, at the end, the acknowledgement to the people who did the calculation, and if you say it in the American way, she cannot help it. She has to, Miss cannot help it, is the one who did the calculation. So that was meant to be the joke and the spoof. Now, what about radiative transfer? See, at one time in the 60s, it became, or in the 40s to 60s, one of the most widely studied subjects among physicists. And you can see the excitement that people had. So this was the translation of a book, a treatise on radiative transfer. Let me read it out, because it's hard to believe the enthusiasm. But it's good to see the enthusiasm that people have. He's no gainsaying that there always exists a scientific discipline which epitomizes the power of human intellect, or a region of exact thought where man's genius shines at its best. For a long time, such was the field of celestial mechanics, woven by great theoreticians whose mathematical analyses still shine with undiminishing brilliance, comparable only to that of the stars themselves. So, I quoted this in the Royal Society because, of course, one of the leaders in celestial mechanics, or the pioneer, was Isaac Newton, who, So to continue the translation, at the present time it is radiative transfer linked to the internal constitution of stars, which fascinates and challenges astronomers all over the world. Among the trailblazers and leaders in this field, none are more profound, none more illustrious than two contemporary astronomers, an American Chandrasekhar and a Russian Sobolev. During this Royal Society session, the last speaker in my session was another Russian astronomer. So he was very happy to see these quotations about, in this field, he is in radiative transfer also. So that's about radiative transfer, okay? A field nothing to do really with electrical engineering except the analogy that I mentioned. Now we come to another field which did not begin as electrical engineering exactly, but which is now a very important part of electrical engineering: prediction and filtering of random processes. And it started with stationary random processes, which are processes whose statistical characteristics do not change with time. Okay. For example, the mean value function is constant. The correlation function, if you know those things, is a function only of the difference of the arguments and so on. Now this goes back, this is also actually a problem in celestial mechanics. It started to predict the movement of asteroids around and ellipses and so on. And it goes back, the method of least squares for solving this goes back to 1800. But we start again now with Norbert Wiener in 1941. Wiener was very anxious, during World War II, a lot of scientists got involved in helping the war effort, especially in radar and sonar and fields like that. Wiener was desperate to do something also himself, but he was a mathematician, so he was wondering what he could do. Actually, it's one of the ironies of history. He made a proposal for modern computing machines, which is similar to that which von Neumann many years later made the first electronic computer. But Wiener's idea was not accepted by the funding agency which funded this work. They said, no, it's not a feasible idea. So Wiener missed the glory of being the pioneer of computers. But then he studied this problem of anti-aircraft fire control. What this is, you have an enemy aircraft coming across over the horizon and attempting to drop its bombs on your target. So by radar, they can measure the location of the plane, and you want to and so you find its position at the present time, you watch it over some time, you want to predict where it will be, say, sometime in the future when it's over the target. So that's the prediction problem. From the past history of the process, predict what the future value will be. Well, you cannot do this exactly because you don't know what it is. But statistically, you can say, the trajectory of the plane, the assumption is that it is a sample function of a random process and a stationary random process. By using the statistics of that and this least squares criterion, mean square error, you can try to minimize the mean square error. The mean means the average over many possible trajectories, and that will give you an estimate of the future position. So that is the problem that he tried to solve. And he was very happily surprised when, in order to solve this problem, he found that he needed a certain equation. Again, it was a mathematically formulated problem. It was the Wiener-Hopf equation came again in this problem. 10 years ago, he had become he was famous for many things already in 1931, but here was this famous equation named after him, was the key to the solution. Moreover, this time, the spectral factorization technique, which was too hard to do in radiative transfer, was easier, because for the engineering problems, as Wiener himself pointed out, you can have rational spectral densities is the approximation, and there the factorization problem is much simpler. And numerically, for the ratio of two polynomials, you can find the zeros and do the factorization. So that was now, as in radiative transfer, Wiener was the pioneer, but his method was not completely practical, and so the actual solution used was different. But nevertheless, Wiener's approach turned out to be important for future development in electrical engineering and in communications. Because for the first time, he made two changes in the approach of electrical engineers. Previously, the design techniques that people had was sort of trial and error. In circuit design, for example, they tried to design a circuit which worked well and solved the problem. But if someone asked you, can you do better? Is there another circuit that has better performance? There was no technique, because what is the measure? What is the objective criterion that you use? Wiener said, let us set up, for any engineering problem, set up a criterion of performance. How do you measure the performance? You make a mathematical criterion, then you find a mathematical solution, and if you do that, then you know that the optimal solution is determined. So there's no trial and error. You know what is the best solution, or even if you don't know the best solution, what is the best performance that you can get? For Wiener, the best performance is what is the minimum mean square error. Even if you can't find the prediction, can you say what the minimum error is, minimum possible error, and then you know whether any other solution that you propose, how close is it to the optimum. So that idea came in from Wiener. And the other idea of Wiener, which was also revolutionary at the time, is that you should bring statistical concepts into the study of the communications process and try to formulate the communication of information as a statistical problem. And later Claude Shannon, partly inspired by these ideas, but developed it on his own, the whole mathematical theory of communication, where these ideas were carried to fundamental limits of channel capacity and how to achieve channel capacity, which many of you are using these days in even your cell phones, and turbo coding and LDPC and so on. So Wiener was important for that work. And here I can show you some equations now. So that was the problem as the following. You have a signal which we call Z or Z of t. You can't observe it directly. There's additive noise, which we'll take as white noise, and you measure Y. And if you know you assume that Z and V are stationary random processes, so Y is also stationary. If you know the mean values, which you can take as 0, and the correlation functions, and you assume that you are measuring over a long time, then the optimal estimate can be found by passing Y through a filter, the optimal Wiener filter W, so the convolution of Y and W, where the impulse response of the Wiener filter satisfies this equation. This is the famous Wiener half integral equation. This is the correlation function or covariance function of the Z process. The noise V is white, so that has a unit spectrum, a constant spectrum, or a delta function correlation. And the unknown obeys this equation. So here you have a convolution. This is a known function. And here is the difficulty. This looks like an easy equation, because let's forget about this constraint for the moment. If this equation is true for all time, you can take the Fourier transform of this, and you may still remember that the Fourier transform of a convolution of two functions is the product of the transform of W and the transform of RZ. The transform of RZ is the spectrum. So it seems easy. So take the Fourier transform, say capital W of omega plus capital W of omega times the Fourier transform here is equal to the Fourier transform there. You can solve it. What's the difficulty? The difficulty is that you have this constraint, that this equation is not true for all time, it's only true for positive time. And this is because of the requirement of causality, that the data that you use is only past data. You cannot have future data. It doesn't allow, prediction doesn't have a meaning. So the Wiener half idea was how to solve this equation with this constraint. Okay? So now Wiener's methods were used actually, and in fact in image processing and so on. these ideas are still used. But around 1960, as you know, the satellites began to be launched. Sputnik was, the Russian satellite was launched in 1957 and shocked the Americans, who decided to, enter the space business themselves. And Wiener's method could not be used so easily for prediction of the trajectory of satellites. And also when you had multiple measurements, instead of observing a scalar, and things changed with time because the satellite was launched not at an infinite past, but at some present time, Wiener's technique couldn't be used. I want to ask, what is the timing that we have for me?
We have plenty of time for you. Let's make this informal. But the original planning was for you to have it 40 minutes. So we have 10 to 15 minutes
left. Okay, so I can speed up or take a little more time.
And then we have a Q&A.
Okay, because if I'm going too slow, please tell me. Okay. But
by the way, do you mind if people ask questions?
No, fine. You can interrupt me. There's no problem. I said I'm not given now. A little more few equations are coming, but I'm not. Okay. But I want to give you the train of thought. Okay. So Kalman changed the formulation of the problem, and he said you still have this y is z plus v. But we have a model for z. What Wiener assumed is that z is a sample function of a stationary random process, and you know its mean value and covariance function or correlation function. Kalman said, no, in the satellite problem, for example, we know from the physics of the problem that, you see, here's the position that, suppose z is the position of a satellite. The satellite obeys Newton's laws, so if you know the position and velocity at any time, by Newton's laws you can predict the future position and velocity. And this is like the F equals ma. This is, anyway, you can have an equation for the evolution of position and velocity, but there is random disturbance, the u of t. So there's a perturbations from the atmospheric effects, the gravity, unevenness, and so on. Those are these disturbances. And this was, of course, the measurement disturbance. So you have this model for the process. You know the statistics of u and v. Try to solve the problem using this information and see what you can get. Well, it was very interesting. One method is, using this model, you can calculate the covariance of z and go back to the Wiener-Hopf equation. But, it's unnecessary. All the information is here. The Kalman filter works directly with this information and gives you a method of finding the future values of x and the future value of any combination of the components of x. X is a vector here. For example, in the satellite, it could be, in the simplest case, x, y, z of position and the x dot, y dot, z dot of velocity. So this could be a 6 vector. And you may be interested only in the x position, for example. Then h will select that first component of x. So this is the Kalman filter. And as you know, it's very widely used now in all fields, including communications. And for example, medicine, where this could be measuring the blood flow parameters through the different veins in the body. And the measurement could be the blood pressure. So how to predict the flow through the artery, through the neck, the carotid artery, using blood pressure measurements? Well, you can formulate that problem this way. And as you know, Kalman got the Draper Prize, which is the biggest prize in engineering, for the Kalman filter. Now, what is the key step in the Kalman filter? Lo and behold, is a Riccati equation, which you may have forgotten, but I mentioned that in 1943, Batsumian found a Riccati equation for the Wiener-Hopf equation. Well, Kalman didn't know about that, but he found again a Riccati equation. And as I said, it's a nonlinear equation. P is now a matrix. with some dimensions n by n, where n is the dimension of the state vector. And again, if you replace this by p of t plus delta minus p of t over delta, you can iterate and get the solution. And the number of flops, floating point operations, to implement one step going from p of t to p of t plus delta, it involves multiplying two n by n matrices together, and that is n cubed. Okay? And so that is a Kalman solution, and it's widely used. Now, the story continues as follows. If you look at this filter, this equation, the amount of work required to carry out one step, as I said, is basically the effort required to multiply two matrices together. An n by n f matrix and this. Now, whether this matrix is the same for all values of time or changes each time doesn't matter. You still have to multiply two matrices together. So the amount of effort is independent of whether the original system was time invariant or not, whether f and q and h depend on time or not. Now that is surprising, because you would think that when the model is constant, then you should get some simplification. But the Kalman filter doesn't simplify in terms of computation. So this is when I fortunately heard a seminar on the Wiener-Hopf equation by a visitor from USC who was working with Bellman in radiative transfer theory. And of course, I told you the Wiener-Hopf equation comes up in radiative transfer theory. So I knew, even though Kalman did not use the Wiener-Hopf equation, I knew that the Kalman filter also solves some Wiener-Hopf equation. So here's the history of it. I became aware of the work of Ambartsumian and Chandrasekhar on Wiener-Hopf equations. I was happy to see that there again they had a Riccati equation. But then I noticed that Chandrasekhar had reduced the burden of the Riccati equation by better exploiting some properties of the radiative transfer problem. This should be there. So my question was, what is the analogy of what Chandrasekhar did in radiative transfer for the Kalman filter problem? Okay. And I found the answer. The simplest analog of Chandrasekhar's result was to assume time invariance of the coefficient matrices, but it turns out you need a special choice of p of 0. I won't give you the details. That's what makes the process stationary, by choosing p of 0 correctly. And now, as with Chandrasekhar, you get a reduction from n cubed computations to n squared. And I mean, just to give you an example, if n is 1,000, n cubed is 1 billion, which is 1,000 million, and n squared is 1 million. So the difference between 1,000 million and 1 million is 1,000 million. Okay. Now, fortunately, in order to get this result for the Kalman filter, I had to invent a different method than Chandrasekhar's for this problem, which was helpful because Chandrasekhar's method only applied to this special problem with a special choice of p. But there are other problems where you may not have that. And it turns out that, so we was able to extend the results to cases where these change with time. And for example, in adaptive filtering problems, H depends on the data that you observe, so it changes with time. So you need these generalized results. But the interesting thing is that new proof depend on a certain identity, which I thought I had discovered. But actually it turns out from studying Bellman's work that a famous physicist, Stokes' law, or Stokes' theorem you may have heard about, in studying passage of light through a pile of plates in 1850, he had this identity. So things are connected to radiative transfer in more ways than one. And one interesting thing is, so we had new applications in engineering, but we also found an application in radiative transfer. because there was a problem in radiative transfer called Lambert scattering, where Chandrasekhar's method did not apply. But because of our generalization, we were able to do it. So we returned something to generalization.
So I think P0 should satisfy something called Lyapunov activity, right?
A P0 is a solution. P0 is the steady state value of the covariance of the state. Yes. Yeah. Yeah, well, actually I can show you the equation. It is the steady state Lyapunov equation. So you are right. So that comes into that situation. But now to move the story forward, the Wiener-Hopf equation is a linear equation. So I began to say, what are some other linear equations to which such techniques can apply? And we found in different applications, integral equations and so on. But what's the simplest linear problem? That's something you think everybody knows. Ax equal to b. A is a matrix which is known, b is a column vector which is known. You got to find the solution x. That everyone knows how to solve this problem. Except that is the problem again the following. If A is an n by n matrix and you have n unknowns, basically you have to solve the linear equations or invert this matrix A, and that takes n cubed operations. And again, if this is a very large matrix, then n cubed is a lot of work. Okay. So how do people avoid that in practice? I mean, if n is reasonable, you can do it. Otherwise, you need big computers. But n can be 10,000 in certain image processing problems. The answer is that in physical problems, you make assumptions, mathematical assumptions, which are not physically true in order to simplify the mathematical model. For example, you assume that, for example, the medium is homogeneous. Its properties, wherever you look in the medium, are the same. Or it's isotropic. In all directions, it looks the same. Time, if the system depends on time, the parameters don't change with time. Signal has infinite duration. Signal has finite bandwidth. We all make such assumptions, but they're not mathematically true. No signal is a pure sine wave, for example. But you assume that your input is a sine wave and so on. What is the point of doing this? Well, they make this matrix A have special structure which allows reduction from n cubed to n squared, or even, depending on the circumstances, n log n or on. Okay. What are these structures? Well, they go by different names in matrix theory. One of the most common is turplets, which is the values along the diagonals are the same. All the diagonals are constant. This is the stationary correlation function. Hankel, Vandermonde matrix, Cauchy, this comes up in many problems in physics. And there are many other special matrices. They all have some structure. The question is how to exploit this structure. Now, and here's where the real nub of the problem. You can believe that if you have a matrix like a Toeplitz matrix, though it's an n by n matrix, 4 by 4 matrix, there are not 16 independent values here. There are only 7, right? So you can, in other words, the order of n is 4, so it's 2 times n, whereas n squared is larger. So you can find a fast way of solving linear equations with this because only so many matrices. But suppose you go to least squares, then the coefficient matrix is really this one, A transpose A inverse multiplied by A. Or sometimes you may have product of 2 matrices. Now, even though A is Toeplitz, this combination is not Toeplitz in general. It's quite complicated. So how do you solve the least squares problem even though you started with a Toeplitz matrix? How do you do it? So composites do not generally inherit the explicit structure of their constituent matrices. Okay. But nevertheless, this is not an arbitrary n by n matrix because it's composed of operations on a structured matrix. So there must be some kind of structure here, though it's not tuplets. It's not constant along diagonals, just as A is or A was. Okay. Now it turns out we found the answer first in continuous time and then moved it to the matrix. It's called displacement structure. And Juan's thesis, Professor Chun's thesis, made an important contribution to it. But let me just explain briefly, but given that the time is over, if people are not interested in the mathematics, I can stop or I can take 2 or 3 slides more. What is your opinion? Okay, so let me just explain briefly. What is this displacement structure? What you have to do is take the original matrix, whatever it is, and subtract from it some modified matrix, which is the following. You have a matrix L, which is called the shift matrix. If you multiply a vector or multiply a matrix by L on the left, as you've shown here, it pushes the matrix. Well, let me do both. If you multiply by L and you think about it, the first row that you get is zeros. The next row, the second row of the product L times this, is actually the first row of the original matrix. So you copy this down, you shift the whole matrix down by 1 position. When you multiply by R, you shift the whole matrix to the right by 1 position. So what happens is when you multiply by L and R, you shift it down by 1 position to the right by 1 position. Effectively, you are pulling it down along the diagonals and leaving 0 behind. That is this. So you have to do this operation. You pull the matrix down along the diagonal and then subtract it from the original matrix. So when you do that, and if you started with a tuplets matrix, there's a cancellation here. Because of the tuplets property, that D is a mistake, or this A is a mistake. This should be A. You get a big 0 there, and you get only 2 elements. So the rank of this matrix is 2 at most. Okay. Now the interesting thing is, suppose you do not start with a tuplets matrix here, but with the inverse of a tuplets matrix. Then when you do this subtraction, you won't get zeros here because this is not a tuplets matrix. It will be a full matrix. But when you calculate the rank, it is still 2. If you take not the tuplets matrix, but the inverse of a tuplets matrix and do this, you'll get a full matrix here, but the rank is still true, 2. So that's the common property. Though a tuplets matrix has an inverse which doesn't look tuplets, nevertheless it shares some property with the tuplets matrix which you might expect, and that is that the displacement rank is still small. It's 2. And now this is true in general. If you have a tuplets matrix and you partition it in this way, then the displacement rank of the original matrix is 2. That's obvious. But the inverse is still 2. If you multiply 2 tuplets matrices together, at most you get 4. If you do this more complicated operation called Schur complementation, it's still 2. And the meaning of it is the following. If a matrix has displacement rank alpha, then instead of O(n) cubed, you can get O(n) squared times alpha. So for the product of 2 matrices, as arises, say, in adaptive filtering problems, you don't need n cubed, even though it's not tuplets, but you need 4 times n squared. So this is the idea that's used to speed up matrix computations. And I'll just jump to my last slide. Oh, sorry, yeah. I said it led to fast algorithms in many fields, including many in electrical engineering, computer networks, mathematics, and so on. But one application was to cell phones, where you can reduce power and get faster processing by doing that. Here are references, and I know that people, I don't know where all these are being used, but I know that Philips is using it, Siemens, and here's a student of mine at Nokia who wrote me a letter that they're using displacement structure algorithms, but you can't use them directly. You have to, as he says, proprietary improvements, each company has their own, for fast parallel implementation, very interesting learning experience to consolidate the conflicting demands of precision, stability, complexity, and real-time constraints into a working receiver structure. So though you have the mathematical solution, you still need engineering judgment and other tools in order to get a real practical solution. But the message is you can start with very abstract mathematics which has to do with the heavens and the sun, and do with problems where you can have your cell phone, which is getting more and more powerful every day, as you know. So thank you very much.